we're going to define a plane in 3-space, and if you recall, in 2-space and in 3-space, basically what we needed was a position vector, and then we needed a couple of direction vectors. So there's our position vector, it's a W. Here's our first direction vector, U. Here is our second direction vector, V. Now we're going to be adding a scalar times those direction vectors to the position vector. My scalars are S and T, which are right over here controlled by these sliders. Here comes the direction vector plus a scalar times the first position vector. So there we go. The tip of this is the result of that. And as you can see, I can basically trace a line. Now, we are going to add to that the second direction vector times the scalar t, and there's the result. Okay, so it's kind of a mess. Now the fact is, I can change the length of the first direction vector using my scalar, and I can change the length of the second direction vector using the scalar. Now I'm just going to sort of do this randomly, and it's going to look sort of confusing at first as I do this. And you know, it depends on how this thing is oriented in space, what this looks like to you. There we go, and over here and down. Okay, so I've done the tracing, and I've got a lot of dots, and I can kind of see a pattern. Now as I rotate this in 3 dimensions, it becomes obvious what that pattern looks like when I reach a certain orientation. As you can see, this is traced out essentially a plane. So that is 2 direction vectors times scalars plus a position vector has basically resulted in a plane. And what you will notice in particular is that that plane contains both of the direction vectors. And so really, if you think about it, it makes sense. That plane contains both of those direction vectors, and of course 2 lines or 2 vectors essentially define a plane. So there we are.